Hello, and welcome back to this lesson in quantitative reasoning. We're in part 2 of 5 of our set applications, our second set of videos for the set unit, and we talked about subsets. So I'm going to remind you of some things you've heard before, but you've probably heard them a long time ago. I remember looking at this stuff maybe even in elementary school, and not all of it maybe, but not always really understanding it. You don't have to have a really huge understanding of the subsets of the complex number system, but I wanted to remind you of some of the words involved. This is one we'll use often. These first three we use a lot. In this class, this last one, not as much. But here, the set of natural numbers, if you were told that your universal set is the set of natural numbers, and those are the only numbers you can use in your answers, it's the numbers we learn to count with. The reason they're said to be natural is because they're the first things we naturally start using as young children. I know with my grandchildren, when we're walking or playing, we count things. 1, 2, 3, 4. It's the first way you use numbers. We didn't start with 0. We don't use halves. We don't use decimals. We just start with the number 1 and start counting. Those are called the natural numbers or the counting numbers. Now, whole numbers are just the natural numbers with a 0 added to the set. In another course I teach, discrete structures, we start counting with 0 a lot. I know that seems kind of funny, but a lot of things start at 0. The reason whole numbers are different than natural numbers and we don't start counting with 0 is the idea of 0, if you go back in the history of mathematics, was not commonly accepted for a long time. We had these natural numbers long before we had the number 0 in our mathematical history. So we have the counting numbers, and they're all positive. 0 is actually unsigned. It's not positive and it's not negative. But then we add to that the idea of negative numbers. So when we use the word integers, integers are whole numbers plus the negatives of the natural numbers. So we'll have these dots mean they go on, start forever. So, negative infinity up to -4, -3, -2, -1, 0, 1, 2, 3, 4, and so on. So it's basically all of these numbers with a negative sign put in front of it added to the whole numbers. Now, we tend to use n to represent natural numbers. We don't have a lot of use for whole numbers. We tend to use z in mathematics when we're talking about an integer. I don't think that appears too much in this course, but I just thought I would point that out in case you see it. And the other two subsets of a couple more subsets of the complex number system I would talk about. The next one is rational numbers. These are all your favorite fractions. Any number that can be created by making a ratio of two integers. So these include positive and negative numbers. And they also include the integers themselves, because if I said write -3 as a fraction, -3 is an integer, and you could write it as divided by a 1. Or you can write it many ways. You could write -6 divided by 2. You could write +6 divided by -2. But you can represent -3 as a ratio of two integers. So that makes all the integers a rational number. All the integers can be represented that way. Numbers like 1/2, 3/5, these are all examples of rational numbers. And it turns out any decimal that has an end, 1.537, that can be written as a fraction. Any decimal that repeats, even if this 7 kept repeating, that can also be written as a fraction. So those are all rational numbers. Don't get too tangled up in the details of that. I just want to make sure you've seen this vocabulary. Don't worry, we do not go into converting decimals to rationals here, although you should all be able to do that. So to wrap up the subsets of the complex number system that are relevant to us, we talked about the rational numbers, and we often use the letter Q to do that. I have that in both slides here, and I have what I talked about here, as far as you can write any integer as a rational number. Real numbers are all the rational numbers plus these strange numbers that can't be written as fractions. So one of those would be pi. So pi is like the famous non-repeating, non-terminating decimal. There's another number like that in math called e. You may or may not have seen that. But there's also things like the square root of prime numbers are irrational. Well, you might punch that in your calculator and you see it says 1.414 something, but it goes on. That turns out it goes on forever and never has a repeating pattern. Real numbers include these. And these numbers here that I've just written are called irrational. So real numbers are made up of the set of rational and irrational numbers. You're not going to be asked to memorize this, but when you see the word real number or the word integer, you should know the difference between those two universal sets. Where you see the word rational numbers and integers, you should know the difference. Now, I've used the words complex number system up here in my slide. What I mean by that is you may have seen in some math class somewhere, and we're not going to do this here, so don't let this send you into a panic mode. Imaginary numbers, like the square root of -1 is not a real number. Unfortunately, they called it imaginary. It is actually a real quantity, and we use the letter I for that. Those would be called imaginary numbers. So when I add the imaginary numbers plus the real numbers, I get what we call the complex number system. We're not going to see any imaginary numbers in here. We're probably mostly going to work with integers, to be honest with you. But I just wanted to make sure you knew the notation and the nomenclature. This is a college math course, so I would like you to, have the vocabulary of a college math student. So those are some things I wanted to get out of the way that the book does not really cover. They just kind of use it. Let's take a look at sets, subsets, and universal sets and empty sets in practice. So this goes back to what we talked about in the last video. Let's look at a couple of examples. The question here is, what is the universal set containing the names of the months of the year? So there are some things I would expect you to know. I would expect you to be able to write out all 12 months of the year. That would be a fair thing to expect you to know in a question. And now the next part isn't as fair. Now they want a subset of the universal set that has only the months with 30 days. Every once in a while I even mix that up. I wouldn't ask you that, but I would maybe say, give me the subset of that universal set that starts with the letter J or something like that. So the universal set containing the names of the months of the year. So there's the names of the months of the year written as a set with braces and commas. Now the subset of this universal set that contains only the months with 30 days is April, June, September, and November. Another subset, I mentioned it. What if I asked you for the subset of the months of the year that start with the letter J? You would write January and June and July. This would be a subset of the months of the year that begin. This would be the months of the year that begin with J. So if I just asked you, give me the set that is the months of the year that begin with the letter J, you would know from the context of that question that the universal set was the 12 months of the year. I wouldn't have to state that out front. I said, give me the months of the year that begin with the letter J. You're not looking at other words or other things or days of the week. You're just looking at January, February, March, April, May, June, July, August, September, October, November, December, and choosing from that. That's the idea of a universal set in the context of the problem. All right, so now let's get into one with numbers. This is math class, right? So what's the universal set containing all the whole numbers 20 through 25? Now, when this word through is used, it does include the ends. If I use the word between, it would not include 20 or 25. But the word through means including the ends. So I'm going to answer this question first, and this answer is here. The universal set should contain all possible whole numbers. See, they use the word between here. I disagree with that. If you say between 20 and 25, you have to use the word inclusive. The word between actually technically means not including the ends. So we're going to have to be careful here with some of our vocabulary. I did not write these slides. They were presented to me when I chose this book, but I want to be careful that I have to go back in and fix that in the actual slide, I think. So the universal set in this case is, the word through is the appropriate word, 20, 21, 22, because containing all the whole numbers. Now, if it had just said the real numbers, you could never write all that, because if it said all the rational numbers, you could never write them all. You just can't do it. So this is very, important that you know what whole numbers means. That's why I went through those definitions. So 20, 21, 22, 23, 24, 25. This answer would have been the same if this word up here was integers, because you didn't start with there were no negative numbers involved. There's no zero involved. So it wouldn't matter whether they said containing whole numbers or containing integers, 20 through 25. So then the next question, determine a subset of this universal set that contains only the even numbers. So I'm not going to write out a whole bunch. I'm not going to start with the number 2 because I'm only concerned with even numbers in this set here that they just had me made. So I take any numbers in this set that end in a 0, a 2, or a 4, and I get this. And notice the set braces and the commas are used correctly. Okay, so that's another practice with universal sets in subsets. That's all I have for this video. In our next video, we're going to talk about finite and infinite sets. There are sets, like the set of real numbers, or even the set of integers, that have an infinite number of elements. And there are other sets, like the set we just dealt with, has a finite number of elements. In other words, it ends. So I look forward to seeing you next video and in class. Thank you.